Hi, everyone. Welcome back. This is Earth and Space Science 101, Lecture 11. So this is our very last lecture of the unit on minerals and rocks. So today is when we're going to finish out talking about sedimentary rocks, and we're going to then continue on to metamorphic rocks. What we're going to do as far as covering sedimentary rocks today is going to look at the other side of sedimentary rock analysis. We have sort of everything that we need from the last lecture to be able to go on to talk about the geologic past. So when I use the term geologic past, it just basically means not yesterday, not the day before that, not 1,000 years ago, but hundreds of millions to billions of years ago. Sedimentary rocks give us a glimpse into this world, and they allow us to understand what the Earth was like at various points through Earth history through looking at the rocks that were deposited at that time. So sedimentary rock analysis allows us to understand past environments, and there are three components to understanding those past environments. Three things about the sedimentary rocks that give us this glimpse into a past world. So the first one that we're going to talk about today is the actual rock type. The rock type itself is going to be really crucial in determining what the geologic history of the area is. As a real kind of brief example, if you have coal in a particular layer of sedimentary rock, that indicates that at some point in the past, you had some kind of swamp environment, some place where you had fresh water and you had lots and lots and lots of plant material that was buried along with that fresh water underneath layers and layers of sediment to eventually form that coal. Now, you can find coal today in places where you don't have very much vegetation at all, places that are almost like desert environments today. But we know at some point in the past they weren't desert-like at all. They were similar to the Atchafalaya Basin that we have today. So the rock type is going to be the first indication, the first clue. The second clue is going to be the fossils that those sedimentary rocks contain. And we're going to talk a little bit more about the history of life and fossils in later lectures when we talk about geologic time. But just to introduce the concept today, a fossil is basically any kind of evidence of life from some point in the past. Some evidence, either the body of the fossil creating some kind of cast, or trace fossils that have been left behind in the rocks. Now, sedimentary rocks are essentially the only type of rock that really contains fossils, at least from our point of view. It is maybe remotely possible for something like an igneous lava flow to record a fossil under the right circumstances. But from our perspective, let's just say that fossils will only really be found in sedimentary rocks. So fossils tell us more than just the history of life. That's sort of the obvious thing that fossils tell us. They give us a little bit of a clue of the depositional environment that sedimentary rock was found in too. In the most simple sense, it can give us an indication of whether that sediment was laid down in a marine environment or a terrestrial environment. So essentially, was that sediment deposited at the bottom of the seafloor or at some point on the continents, like maybe in rivers or lakes? So fossils give us a lot of information about the rock. Now, we have two basic types of fossils, as you can see in some of these pictures. We've got things called body fossils. So essentially, if I were to wander out into Lake Pontchartrain, lose my footing in the mud, slip, fall, die, eventually the sediment would be deposited on top of my body, and it may create, under the right circumstances, an imprint of my body in the fossil itself, especially the imprint of something like maybe my bones. Also, potentially under the right circumstances, maybe even my bones would become recrystallized. Things like silica and calcium would replace some of the elements in my bones, and it would actually fossilize my bone structure. So under that circumstances, I would become a body fossil. So the body fossils that we find in sedimentary rocks are of animals and plants, potentially maybe things like fungus as well. And these body fossils give us some sort of indication of what the organism actually looked like. And the easy way of being able to tell body fossils from trace fossils is, of course, the organism has to die to create a body fossil. So whenever you see things like seashell imprints, the trilobites that you can see in one of these images here, these are all body fossils. Trace fossils are a better indication of an organism's behavior. These are things like essentially footprints, burrow imprints, traces of the organism as it moved through the sediment that were then later recorded. So the trace fossils tend to be a lot more plentiful. A lot more abundant, and they give us a little bit better indication of the behavior of particular organisms. They also, along with body fossils, give us an indication of the depositional environment. So all fossils are really good indicators of depositional environment and the geologic history of the area. The last thing that we're going to talk about that gives us a pretty good indication of what was going on in an area that's recorded in the sedimentary rocks as they form are things called sedimentary structures. So in the most basic sense, sediment basically wants to be deposited flat along the surface of the earth. When you have mud settling out of a lake to deposit on the floor, whenever you have sand coming to rest on the bottom of a river channel, typically that sediment is deposited in nice flat layers. And we call those sedimentary beds. So bedding is one type of sedimentary structure, but not all bedding has to be exactly horizontal. It can be angled, so you can have things called cross beds, and you can have other things that happen as the sediment is deposited that leave some sort of pattern behind. Geologists have the ability to recognize these patterns and compare them with how sediment is deposited today on Earth and give us a little bit of an indication of what was going on in that area potentially hundreds of millions of years ago. So as I said, bedding is a really straightforward geologic structure, basically the most common type of structure. You have things called laminar beds, and those are basically flat beds. But you can also, under the right circumstances, have cross bedding. The image on the right is of some cross-bedded sandstone, and that sand was deposited in big wind-blown dunes, like in the Sahara Desert today. So you get these really, really large, beautiful cross beds in that kind of case. And that, looking at that picture and recognizing what that means, it can really only indicate one depositional environment. Wind-blown sediment and things like sand dunes in a desert-type environment today. So again, all of this is to give us an idea of what was going on in the geologic past. Other sedimentary structures include things like ripple marks. They can be symmetrical or asymmetrical. So essentially on either side of the ripple, you can have the same overall size of the crest on either side of that ripple, or not the same size crest, symmetrical or asymmetrical, and those indicate different depositional environments. You can have things like graded bedding, which gives you the idea that whatever was moving that sediment is losing energy because it's depositing more fine-grained sediment from the bottom up. You could have the reverse of that happening. It's still graded bedding where you have more energy. So let's say maybe something like a river starts flowing faster, and then it's able to move more coarse-grained sediment. So the sediment actually coarsens upwards instead of fining upwards. Both of those would be examples of graded bedding. Mud cracks are a really good sedimentary structure that indicates the climate in a particular area. If you have mud deposited in the first place, then most likely this at some point was underwater. But if you have mud cracks forming, that means that mud had to dry out in order for that to form. And again, under the right circumstances, those structures can be preserved. So we can record in the geologic past that drying event, that change in climate that created these structures. So sedimentary rock interpretation really comes down to those three things: rock type, fossils, and sedimentary structures. And we can use all of these to understand the geologic history of an area. Now, all of this is pretty abstract at this point, so I want to take you on a little field trip that's going to show you how we're going to use these things to a little bit better advantage, how we can actually interpret the geologic history of an area using these features that are found within sedimentary structures. So I hope you enjoy this. Today we're going to go to a truly beautiful location in the southwest of the United States. We're going to Zion National Park. This is located in southwestern Utah. There is a particular really famous hiking trail in Zion called the Angel's Landing Trail. And from that trail you can view these amazing cross-bedded sandstones. So most of the time when we see cross-bedded sandstones, they're very, very small in scale. You know, they may be only like a few inches in scale, but these are several feet in scale. And Zion's not the only place where you see these really large-scale cross-beds like this. So the reason why we're going to this location today is to do a little bit of a depositional environment analysis, something that we talked about in the lecture before. We can use some of these factors that we can see here, and those factors, to remind you again, are the rock type, any fossils that might be present, and the sedimentary structures, in order to identify the history of this area at this particular time. So at the time when these sandstones were being deposited, which was in the Jurassic period, this entire area was actually very, very dry. Most sedimentary rocks form underwater, but you do occasionally get some that are actually wind-blown sediments. And we think the reason why that these cross beds are so large is because of the wind-blown nature of these dunes. We call it these aeolian deposits. They're wind-blown sand dunes. So unlike the smaller crossbeds that you get when you move sediment in, say, something like a river, you get these very, very large crossbeds instead. And this is some of the best and easiest viewed crossbed sandstones anywhere in the world. So that's going to wrap up sedimentary rocks for us. The last thing that we have to talk about in this unit is our third overall type of rock. It's the one that's the most abstract to think about. These are metamorphic rocks. We call them metamorphic rocks because they have been metamorphosed. To metamorphose something basically just means that you're going to change that substance. Now, there are a lot of things that could fall into this definition of changing something, but most importantly, most of the processes that are going to form metamorphic rocks require solid state changes. You can't have anything more than at least maybe partial melting of the rock and have it still be considered a metamorphic rock. Now, we have to compare this for a second to the rocks that we've already talked about. Igneous rocks require completely melting the rock and resolidifying it. So when you cool and solidify lava or magma, you form igneous rocks. Sedimentary rocks require surface conditions. So you have to break those rocks into pieces, put all those pieces back together again to form a sedimentary rock. Metamorphic rocks are sort of in a gray area between the two. They have been metamorphosed, and the thing that it will do, this changing or metamorphosing, is an increase in temperature and pressure with depth. But if you have too much depth and too much of an increase in temperature and pressure, you'll melt the rock. So you have to kind of work within this very particular range of temperatures and pressures in order to form metamorphic rocks. So metamorphism is all about solid state changes. While there is some partial melting that can happen to create some of the rocks that you're seeing in these pictures with that really pretty sort of white banding, some of that has actually been melted and resolidified, but the rest of the bulk of the rock has not been melted and resolidified. So because there's only partial melting, not complete melting, it still falls under the definition of a metamorphic rock. You get entirely different textures, an entirely different look to the rock than if you had completely melted it and recrystallized it. Now, the first thing that we're going to talk about with regard to metamorphic rocks is what is going to create the different textures we see and what is going to influence the composition we see. So you may have picked up on this trend already, but when we've talked about all of the different types of rocks, igneous, sedimentary, and now metamorphic, understanding the differences between these rocks and classifying them really all goes down to composition, what the rock is made out of. That's our first basis for classification, and texture. So we're going to do the same thing with metamorphic rocks, except we're first going to talk about what is going to influence those factors. So the composition of the metamorphic rock is mainly going to depend on the composition of the parent rock. And this is probably one of the most simple concepts we'll learn in all of geology and in all of rock analysis. What you have to start off with is what you're ultimately going to end up with. The only difference between the parent rock, the stuff that was changed to form the metamorphic rock, the only difference between that parent rock and the daughter rock is going to be that you've essentially cooked the rock and recrystallized it, but the same ingredients are there. So my favorite analogy with this and with most things is the food analogy. If you have a cookie dough that's composed of chocolate chips and flour and sugar and baking powder, then you're going to have a chocolate chip cookie. You have all of the right ingredients to form that chocolate chip cookie. You can't take that cookie dough and form like an oatmeal raisin cookie out of it. You don't have the right ingredients. You'd have to change the ingredients, change the parent product in order to influence the daughter product and to be able to get something like an oatmeal raisin cookie out of the deal. So a good example of this is what happens when you metamorphose the sedimentary rock limestone. Limestone is primarily composed of really only just one mineral, calcium carbonate. We call it calcite. So that limestone's going to have a texture that's reminiscent of the way that it formed. It might even still contain lots of fossils. But once you subject that limestone to the increase in temperature and pressure that happens with depth, once you bury it deep enough and recrystallize it, then it's not going to melt, but it's going to recrystallize to form the rock marble. So all marble is, like in marble countertops or marble sculptures, all marble is going to be a metamorphosed limestone. So you cook it enough, you recrystallize it, you really change what it looks like, but it's essentially composed of the same minerals still. So we might have a little bit of a change in the mineralogy of these rocks from parent to daughter in some examples, but you still have essentially the same ingredients. You still have all of the same elements present. If you have calcium, carbon, and oxygen present to begin with in your limestone, then you can really still only make minerals, and you can really only still make the rock out of those same ingredients still. You're not going to be able to just sort of find silicon and aluminum and all of these other elements just out of nowhere. So the single most important thing that controls the composition of a metamorphic rock is the parent rock's composition. Texture is going to be a little bit more interesting because texture is going to be dependent upon a few different factors. Obviously, temperature and pressure, which both increase with depth. But you don't always get metamorphism with depth. It's not like you have this depth with under the surface of the earth where all metamorphic rocks are going to form. Metamorphic rocks are primarily going to form in conjunction with mountain building. So the second thing that's going to influence the texture of metamorphic rocks is going to be the effect of tectonics, particularly compressional stresses in conjunction with convergent plate boundaries are going to be really good at forming metamorphic rocks. So let's look at all three of these factors: temperature, pressure, and the effect of tectonic forces. These are all, again, going to affect the texture of the metamorphic rocks. Temperature is going to be one thing that's going to affect the types of minerals that you see present within a rock. If you start out with something basically like a mudstone or a shale, it's composed of clay minerals. If you increase the temperature enough, then those clay minerals are no longer stable. If you remember, those clay minerals initially formed because of chemical weathering on the Earth's surface to form something that was more stable at the Earth's surface. So it falls into reason if you reverse that process and subject it to an increase in temperature, those minerals are no longer going to be stable. They've rearranged themselves a little bit into a configuration that's more stable at a higher temperature. So once you exceed that temperature range, new minerals form. And the same thing happens with pressure. Pressure, like temperature, is going to be something that increases with depth. And pressure is going to really be exerted on the rock and on the individual minerals from all directions. So this image that accompanies this is going to show you a pretty good indication of what happens when you have an increase with depth. Except in this example, it's going to be an increase in depth in the ocean. If you have something exposed to surface temperature and pressure, it might act in one particular way. But if you put it 100, 200, 300 feet below the surface of the water, it's not only experiencing the pressure from all of the weight of the water overlying it, it's also experiencing the weight of the water pushing in on it from all sides and from all directions. So that's the main difference between pressure and a stress. Pressure is equal in all directions, whereas geologic stresses are unequal. They're only coming in from particular directions. Compressional stresses and tensional stresses and shear stresses, those are all basically forces that are not coming in from all directions, but only some directions. So the effect of pressure is going to be to make minerals a little bit more dense. So when you increase both temperature and pressure, you're going to get typically new minerals forming, and those minerals are going to configure themselves in a more highly packed, compacted sort of configuration. The last factor that's going to affect the texture of metamorphic rocks is going to be the effect of tectonic forces. Tectonic forces are, again, unequal forces. They're stresses. Primarily in this case, we're going to be talking about compressional stresses and shear stresses. So a quick reminder from a few lectures ago, lecture 2, when we talked about these stresses, a compressional stress is when you push on something from either side and squeeze it. A shear stress is going to be when you take two things and slide them past each other. And both of these are really common in mountain building and really common in convergent plate boundary environments. So in a little bit later, we're going to talk about how plate tectonics relates to metamorphic rocks in more detail. But for now, just know that those stresses are the primary reason why most, not all, but most metamorphic rocks experience foliation. So one of the most beautiful things about metamorphic rocks is that they tend to be banded. Unlike something like an igneous rock or even sedimentary rocks, you have an alignment of the minerals in one particular direction. And sometimes those layers are sort of folded in on each other. Sometimes they're not. But most metamorphic rocks do have some degree of foliation or an alignment of the minerals in one direction. It's what happens as a result of taking these minerals and exerting a stress just in one direction. You tend to squeeze them and align them to be flat in that direction. So that's our primary way of classifying metamorphic rocks. Now we're going to move on to classification. The basis for classifying metamorphic rocks is first to talk about whether they're foliated or non-foliated. Now, I've referred to this before, but it's helpful in a lot of cases with rock analysis to be able to look at rocks under the microscope. So what you're seeing in these images are rocks that have been sliced and taken a little tiny thin slice, so thin that light can actually pass through the rock itself, and then they've been put under the microscope so you can take a picture of them. In the case where the rock itself is non-foliated, you could see it under a microscope and sometimes often in hand sample as well, that there is no clear alignment of the minerals in any one particular direction. If the rock is foliated, then the minerals that are kind of flat and platy, they are going to align in one particular direction. So you can see in these images which one's foliated, which one's non-foliated, and the direction of the foliation in the foliated sample. So that's our first basis. We take all of metamorphic rocks and we're going to basically say they're either foliated or non-foliated. Whether or not they're foliated or non-foliated often, not always, but often gives us an indication of what type of environment, what type of metamorphism has taken place to form those rocks. So non-foliated metamorphic rocks, again, contain no alignment of the minerals in any one particular direction, either because the minerals aren't very flat and platy, so they don't tend to align in that direction at all, or because there was no tectonic stress that resulted in this rock's formation. So we'll talk about that distinction in just a minute here. So in non-foliated metamorphic rocks, these typically include things like quartzite, which is the metamorphic equivalent of a sandstone. It's rich in the mineral quartz. Or things potentially like marble, which is the metamorphosed equivalent of limestone. So in both cases, they don't have any particular alignment of the minerals in one direction. You're just further classifying these by their composition. Foliated metamorphic rocks are going to, again, have that foliation, so they're going to have that alignment of the minerals in one particular direction. And as you increase the temperature and pressure that these rocks have been subjected to, you increase the degree of metamorphism that has taken place. So all of these names that we give for the type of the type of foliation that can be found in these rocks is indicative of the temperature and pressure in which they formed. Things that have a slaty foliation, so the rock slate, would be a rather sort of low degree of metamorphism, whereas something like a schist or a gneiss would indicate a rather higher degree of metamorphism has taken place. So contact metamorphism is our first of 3 overall types of metamorphism. And this is the one that's going to most often result in rocks that are going to not be foliated. Now, contact metamorphism is referring to what is actually creating this metamorphic rock to begin with, which is contact with some sort of hot source underground. So this is the most common scenario in which you're going to form contact metamorphosed rocks. If you have a rising magma plume, so you have this body of hot molten rock underground, it's moving up towards the surface, and it's slowly cooling and solidifying, it's basically like this furnace underground, and anything that comes close to it is going to be cooked on contact, like scrambled eggs on a frying pan. So anything that comes in contact with these rocks is going to be cooked, but not necessarily completely melted. So if that hot magma underground comes in contact with something like a sandstone, it will recrystallize it and metamorphose it to form a quartzite. If that hot source underground comes in contact with something like limestone, you're going to form marble as a result. You recrystallize the rock that magma comes in contact with. So that's why it's called contact metamorphism. So non-foliated metamorphic rocks typically are going to be more closely related to contact metamorphism. Regional metamorphism requires an increase in both temperature and pressure. So this is going to be a lot more widespread and something that's going to happen in conjunction with mountain building and with convergent plate boundaries. So this picture that's going to accompany this material is one of the most helpful in the entire chapter on metamorphic rocks out of your textbook. It shows you an increase in the degree of metamorphism as you go from closer up to the surface where there is no metamorphism taking place. You have folded, unmetamorphosed sedimentary rock all the way down to the bottom where you're going to have completely melted rock. So as we go from the top down, we're increasing the grade of metamorphism that's taking place. We go from a low-grade metamorphism with things like the slate and the phyllite. Those are going to look fairly similar to the rock from which they came. So things like a shale would first metamorphose at a higher temperature and pressure and depth to form something like slate, and then it would form a phyllite. And as you keep increasing the temperature and pressure, you go into some of the higher metamorphic grades. So you would form things like various types of schists, garnets might start to form and crystallize, and eventually something like a gneiss and even a migmatite. Both of those would require some partial melting to take place. So that would require the highest degree of metamorphism. Finally, if you go below the extent of this picture, you would reach such high temperatures and pressures that the rock would be forced into a completely molten form. And once it did that, then that melt would start to move up towards the surface, because as soon as you melt something, you are going to decrease its density. And so then it wants to float. It wants to move up towards the surface because it's lower in density than the surrounding rock. As that rock then cools and solidifies, it can contact metamorphose everything around it. So regional metamorphism typically happens at convergent plate boundaries. That's where you have all of the conditions necessary in order to metamorphose the rock. You have an increase in temperature and pressure with depth. You've thickened the crust, so it's actually possible to get enough of an increase in temperature and pressure for that rock at depth to start to recrystallize. Plus, you have all the compressional and shear stresses from the collisions of those two plates. Now, the convergent plate boundaries that are more often going to be associated with regional metamorphism are going to be oceanic continental convergence or continental continental convergence. Only in those two cases do you typically get the crust thick enough for metamorphism to take place. So at oceanic continental convergence, as you can see sort of pictured here, as that oceanic crust subducts underneath the continent, you get high pressure and eventually you get high enough temperatures in order for certain minerals to form. You get a completely different sequence and a different suite of minerals forming at these environments than you do at continental convergent plate boundaries. So at continental convergent plate boundaries, you're going to have an overall much thicker crust, and it's possible to go through the entire suite of metamorphic rock types, all the way from taking something like a shale, which is your unmetamorphosed sedimentary rock, and turning it into a slate, a phyllite, a schist, a gneiss, all the way through the entire sequence from low grade to high grade metamorphism. So regional metamorphism is the most widespread, it's the most common type of metamorphism. Contact metamorphism is somewhat common, but not as much as regional metamorphism. And then we're going to talk about a third type of metamorphism that's extremely rare, but very, very interesting. It's a case where you're going to have high pressure, but you're not going to have as high of an increase in temperature. So by definition, if we're not increasing temperature at the same rate that we're increasing pressure, we can't be talking about subjecting rock to an increase in depth within the Earth's surface. This has to be something that's actually happening at the surface of the Earth. And really the only case I know of where metamorphism is actually taking place at the surface of the Earth. The other thing that's really different about this type of metamorphism than the others that we've talked about is, unlike the others, which require millions of years to have rocks undergo this transition, this can happen rapidly. This can happen in the span of seconds to minutes. This is called shock metamorphism, where something, and I'm alluding to this in the future here, we're going to get to this in just a minute, something is going to happen so rapidly at the Earth's surface that requires such a high increase in pressure that you're going to form metamorphic minerals as a result of this rapid application of pressure. The only thing that can actually make this happen on the Earth's surface is a meteorite impact. So shock metamorphism is exclusively going to happen at impact sites and impact craters. So essentially, as you have some piece of debris from space, something left over from planetary formation, some big chunk of rock and metal in space, a meteorite, as it moves through the Earth's atmosphere, it might shrink up a little bit. It might slightly be broken apart. That's what creates a meteor shower, is that breakup of the rock coming into the Earth's atmosphere. But once it ultimately comes to hit the Earth's surface, it can create a very large crater and a huge region where anything that was exposed at the Earth's surface is going to be recrystallized because of this rapid application of pressure. So really, really cool things happen at these impact craters. You can find a really weird variety of quartz. Any sand that was exposed onto that surface would be transitioned to this weird variety of quartz that you only see at these impact craters. It's a variety called stishovite. So it's a high pressure, low temperature equivalent of quartz. It's even possible to form things like diamonds in these impact craters. They're very, very small, very, very weird diamonds. Most diamonds are octahedral. They would look like maybe two pyramids resting on top of each other if you didn't actually cut that diamond up. But in these environments, they typically form a hexagonal structure. So it's a weird structure of diamond that only forms at these impact craters. So you really have a whole suite of very, very unique, very special minerals that only form in these environments. So that's our last type of metamorphic. That's our last type of metamorphism, and the end of our whole talk on metamorphic rocks. So that also means that's the end of talking about minerals and rocks in general. So you did it. You made it through. We're next going to talk about water on Earth in Unit 3. So I hope you enjoy that as well. Until then, keep rocking.